Is the universe infinite? People ask this question all the time. And the honest truth is that the answer depends on something we still do not fully understand. It depends on how much matter exists in the universe and how strong gravity truly is. But while there are things we do not yet know, there is also a great deal that we do understand. And what the mathematics predicts is far stranger and far more unsettling than most people expect. Space itself is expanding right now. This is not an idea or a theory in the casual sense. It is an observed fact. Galaxies billions of light years away are moving away from us at enormous speeds, thousands of miles per second. And the farther away a galaxy is, the faster it is receding. It is not that galaxies are flying through space. It is that space itself is stretching, carrying galaxies along with it. The fabric of the universe is growing. Every second, the universe becomes larger. You cannot feel it here on Earth. The effect is far too small at our scale, but it is real, and it has profound consequences. If space is expanding today, then in the past everything must have been closer together. If you run time backward, galaxies approach one another. The universe becomes denser, hotter, more compact. Go back further and further, and eventually every galaxy, every star, every atom converges into the same place, compressed into a state of unimaginable density and temperature. That moment is what we call the Big Bang. Not an explosion that happened at one point in space, but the expansion of space itself. The moment when space, time, matter, and energy began. This conclusion did not come from philosophy. It came from observation. In the early 20th century, astronomers began studying distant galaxies more carefully. They analyzed the light arriving from these objects and noticed something peculiar. The light was not the color it should have been. It was shifted toward the red end of the spectrum. This effect became known as redshift. At first glance, it might seem unremarkable. Light changes color for many reasons, but this shift followed a precise pattern. The farther away a galaxy was, the greater its redshift, not randomly. Systematically, when an object moves away from you, its light stretches. The wavelength increases. This is similar to sound. When a car passes you, the pitch drops as it moves away. Light behaves in the same way. Motion stretches the wavelength, shifting it toward red. The implication was unavoidable. Distant galaxies are moving away from us, and not only that, they are moving away faster the farther they are. This could only mean one thing. Space itself is expanding. And it has been expanding since the beginning. But this discovery raised an even deeper question. If the universe is expanding now, what will happen in the future? Will it expand forever? Or will gravity eventually slow it down and pull everything back together? The answer depends on a balance. Everything in the universe has mass. Mass creates gravity. Gravity pulls inward. It resists expansion. Even as galaxies move apart, gravity is constantly trying to bring them back together. The situation is similar to throwing a ball upward. If you throw it gently, gravity slows it down, stops it, and pulls it back. If you throw it at just the right speed, the escape velocity, the ball continues rising forever, slowing more and more, but never falling back. And if you throw it faster than that, it escapes easily and never returns. The universe behaves in the same way. Its fate depends on how fast it is expanding compared to how strongly gravity pulls inward. From this balance, three possible futures emerge. In the first scenario, expansion wins. Space expands too quickly for gravity to slow it down. Galaxies continue to race away from each other. Over time, they become so distant that light from one galaxy can never reach another. Each galaxy becomes isolated, alone in an ever-darkening universe. Stars burn out one by one. Energy dissipates. The universe grows colder, darker, and emptier, not with a dramatic collapse or explosion, but with a slow fading into silence. A universe where nothing interesting can ever happen again. In the second scenario, expansion and gravity are perfectly balanced. Space continues to expand forever, but more and more slowly. The expansion rate approaches zero as time stretches toward infinity. The universe remains balanced on a delicate edge, neither collapsing nor accelerating away uncontrollably. In the third scenario, gravity wins. Expansion slows, then stops, and then reverses. Galaxies stop moving apart and begin moving toward each other. Space contracts, density increases, temperature rises. Matter is compressed. This is the big crunch, a reversal of the Big Bang. Galaxies collide and merge. Stars are torn apart. Eventually, atoms themselves can no longer exist. Matter collapses into a single dense state once again. A universe that began in fire ends in fire. Which of these futures is ours? The answer depends on how much matter exists in the universe, including matter we cannot see directly. And while thinking about this question, another realization emerges. If the entire universe can collapse under gravity, what about smaller objects? What about individual stars? Stars appear eternal when you look at the night sky. They shine steadily, night after night, century after century. But this stability is an illusion. Stars survive only because of a delicate balance, and that balance does not last forever. At the core of every star, nuclear fusion is taking place. Hydrogen atoms are forced together under immense pressure, forming helium. In the process, energy is released. That energy pushes outward. Radiation pressure fights against gravity, which is constantly trying to crush the star inward. As long as fusion continues, the star remains stable, but nothing in the universe burns forever. Eventually, a star begins to run out of fuel. Hydrogen in the core becomes scarce. Fusion slows. The outward pressure weakens. And when that pressure fades, gravity begins to dominate. What happens next depends on the mass of the star. For smaller stars, stars like our sun, the end is relatively gentle. As fusion slows, the star expands briefly and then sheds its outer layers. What remains is the core, a dense, Earth-sized object called a white dwarf. It no longer produces energy. It simply glows from residual heat, slowly cooling over trillions of years. Eventually it becomes a cold, dark remnant, a stellar corpse, but massive stars follow a far more violent path. When fusion stops in a massive star, gravity takes over almost instantly. The core collapses catastrophically. In a matter of seconds, the inward pull becomes overwhelming. Electrons are forced into protons. They combine to form neutrons. The core becomes a neutron star. A neutron star is one of the most extreme objects in the universe. It is a sphere of pure nuclear matter, only a few kilometers across, yet containing more mass than the sun. The density is beyond ordinary comprehension. A single teaspoon of neutron star material would weigh as much as a mountain. Gravity at the surface is so intense that if you dropped an object from a height of 1 meter, it would strike the surface at a significant fraction of the speed of light. Time itself slows dramatically near such an object. An hour on a neutron star passes more slowly than an hope. Are far away, yet even neutron stars have limits. There is a maximum mass they can support. Beyond this limit, known from theoretical calculations, neutron pressure is no longer enough to resist gravity. If the mass exceeds this threshold, collapse continues. And this is where the universe becomes deeply strange. To understand what happens next, we must turn to the mathematics of gravity itself. The equations that describe gravity in extreme conditions. These are the equations of general relativity. For planets, stars, and even neutron stars, they work perfectly. They predict how space curves, how time flows, and how matter moves. But when matter is compressed beyond a certain density, the equations reveal something unexpected. A critical boundary. A point beyond which the behavior of space and time changes fundamentally. For any object of a given mass, there exists a critical size. If the object is compressed below this size, gravity becomes so strong that nothing can escape. Not even light. This critical size is known as the Schwarzschild radius. For the Sun, this radius is about 3 kilometers. For Earth, it is roughly the size of a marble. Normally, stars and planets are vastly larger than their Schwarzschild radius, which is why nothing unusual happens. But if a massive star collapses far enough, its actual size can shrink below this critical boundary. When that happens, something extraordinary occurs. From the outside, the collapse appears to slow down. Light leaving the surface becomes redder and dimmer. This is gravitational redshift. Light climbing out of a strong gravitational field loses energy. Its wavelength stretches. As gravity increases, this effect becomes more extreme. Time itself is affected. To a distant observer, the collapsing star appears to slow as it approaches the critical radius. Movements on its surface take longer and longer to complete. A wave of a hand stretches into minutes, then hours, then years. Eventually, the image freezes entirely. From the outside, the star never seems to finish collapsing. It appears frozen at the boundary, suspended forever. Time, from that distant perspective, has stopped. This is why early descriptions referred to such objects as frozen stars. But this is only half the story. To understand the full reality, we must consider another perspective. The perspective of someone falling inward with the collapsing star. From their point of view, nothing unusual happens at the boundary. Time flows normally. Their watch ticks as expected. There is no sudden shock, no warning sign, no dramatic event. They pass through the critical boundary without noticing it. Once inside, however, something has fundamentally changed. Every possible path forward leads inward. There is no direction that leads out. Signals cannot escape, not because they are blocked, but because space itself is curved so severely that outward paths no longer exist. Escape becomes impossible. From the outside, the falling observer appears, ours frozen forever. From the inside, the observer falls freely, reaching the center in a finite amount of time. Both descriptions are correct. They are simply two different perspectives on the same physical reality. Time flows differently depending on where you are. This is not science fiction. It is measurable fact. Even on Earth, time runs slightly faster at your head than at your feet, because gravity is weaker higher up. Over a human lifetime, the difference is tiny but real. In strong gravitational fields, the effect becomes dramatic. Near neutron stars, time slows significantly. Near the Schwarzschild boundary, from a distant perspective, time effectively stops. These collapsed objects emit no light. They are invisible, yet their presence can still be inferred through their gravitational influence on nearby stars, through the bending of light from distant sources, through distortions that reveal something massive and unseen. Physics does not allow us to ignore these predictions simply because they are uncomfortable. If the mathematics leads us here, then this is where understanding must go. Somewhere in the universe, massive stars are collapsing right now. Gravity is crushing inward, past boundaries we cannot directly observe. From one perspective, time freezes. From another, it flows uninterrupted. Reality does not belong to a single point of view.